Hello. Hello, everyone. Right. So how many people do we have today? 15. Okay, brilliant. Okay, so apologies for the late for being late with the third maths with the third assignment. Hopefully it will be on today. We just reread it, found something we don't like, we changed it, then we found something else we don't like, we changed it again, so it just takes time. All right, so how do I spotlight for everyone? Okay, so everyone should see me now. So the third assignment is on derivatives. And why derivatives? Well, the derivative is an extremely powerful tool for a physicist, especially for a physicist, but of course for a mathematician as well. It allows you to understand the behavior of functions. And if you recall, the derivative of, for example, the displacement in physics is the speed. Yes, if you differentiate the displacement with respect to time, you get speed. And if you differentiate the velocity with respect to time, you get acceleration. So lots of things. So let's jump right into it. I'll share my screen as usual, and hopefully introduce you to the derivative. And just one more thing, so you can see the chat. You can see the chat. Ah, hello. Yes, brilliant. Can people see my screen? Yes. Okay. Good. Yeah, that's fine. If you don't see my screen, type no. So the first question is find the derivative of y equals x cubed from the first principle. But before we attempt this, well, I need to explain what the derivative is in the first place. So let's say you have a graph of a function. You have a graph of a function, and it goes something like this. The derivative at this point, the derivative of the point x, it's the instantaneous rate of change of the function. The rate of change. So this is y, this is x, the rate of change. So basically, we're interested in how fast the function is increasing or decreasing. So you could see here, the rate is quite steep, is quite high, and here the rate is not as high. So the instantaneous rate of change. To do this, we will take a point on the graph, x. And this is, of course, f of x, because the graph of the function is y equals f of x. We go to the right and take another point. And we make a step to the right, step of size h. And this point is going to be x plus h. So h is the step. So basically, we're interested in how far up we go if you make a step to the right. And you know that this is called gradient. This is called the gradient of the function. And here, similarly, we're going to have f of x plus h. Then we draw a line. We draw a line, and we want to find the gradient of that line. the gradient of that line m is change in y over change in x. So change in y over change in x. Change in y is this value. So it's going to be f of x plus h minus f of x. So that's this is delta y. And this is delta x. Well, delta x, you can immediately see that delta x is h. Or you can say it's x plus h minus x. So x plus h minus x, which obviously is h. So we can simplify that, cross this out. So this is the gradient of that line, f of x plus h minus f of x divided by h. Now the derivative of the function is so f prime x, or f strive x, f dash x, there are many names, is the limit of this value, the limit of f of x plus h minus f of x divided by h, as h tends to 0. Okay. Can I get a quick answer in the chat? If you understand everything up to this point, please type 1 in the chat. If you don't understand everything up to this point, type 0. All right, very nice, very nice. So what does it mean that the limit of as h tends to 0? Well, we make h smaller. That means the line becomes like this. If we make h smaller, it becomes like this. Then we make it smaller yet. Okay. And smaller and smaller. And at some point, the line becomes the tangent. The gradient of that line becomes equal to the gradient of the tangent. What's this? So what it says here, the limit of this expression, and this expression is the gradient of the line, tends to the gradient of the tangent at this point. Okay, so this is the definition of the derivative function. And let's use that definition to find the derivative of x cubed from the first principles. So what we do is we say f of x, sorry, I don't like red, f of x is x cubed, of course. We also need f of x plus h. So f of x plus h plus h is, of course, x plus h cubed. And let's plug it in. So the derivative of f is equal to the limit as h tends to 0 of the expression f of x plus h, so x plus h cubed minus x cubed divided by h equals limit h tends to 0. Now we use the binomial expansion to expand x plus h cubed. So it's going to be x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed divided by h. X cubed cancels out, and we're left with and we divide by h. Yeah, we divide by h, so it's going to be limit as h tends to 0 of, so h kind of cancels. This becomes 2. So it becomes 3x squared plus 3xh plus h squared. But we know that h tends to 0. H tends to 0. So this tends to 0 because as h tends to 0, this thing becomes smaller, smaller, and smaller. And this also tends to 0. And nothing happens to this one. So the limit is equal to 3x squared. Okay. Now, on a scale of 0 to 10, how well do you understand what I have done? Oh, very good. I'm impressed, guys. Okay. So let's knock it. Let's knock it up. Is that an expression? Is that what people say? Anyways, find the derivatives of sine x and sine 4x from the first principles. Look, the thing here, that here you could just plug in h equals 0 and you got the answer, 3x squared, if you just substitute. But sometimes you can't do that. Let's say you need to find the limit as x tends to 0 of x divided by x. Oh, you can't plug in x because you can't. It will be 0 divided by 0. That's nonsense. Yeah, you're not allowed to divide by 0. Okay. And so what do? Well, intuitively, you know that this expression is 1 because x divided by x is 1, except when x is 0, because when x is 0, it's undefined. But this limit is equal to 1 because as you approach 0, this expression approaches 1. So what does that mean? Well, let's look at a graph. Y is equal to x divided by x. And obviously, you see it's 1. I mean, it's the same as y equals 1. It's the same graph because you can simplify. But with the one exception, look, as we get closer to 0, sorry, y is 1, 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 except this point. It's undefined when x is 0. But the limit is still 1 because no matter how close we get to 0, y is still going to be 1, except in the actual point 0, where it's undefined. So we say the limit of x over x as x tends to 0 is 1. And we have some more important results. The limit of sine x divided by x. L'Hopital's rule relies on derivatives, and you kind of can't use the derivative to define the derivative, if that makes sense. Right. A very useful limit is this, sine x over x. And let's look at the graph of sine x over x. You'll need to look it up. Sorry, guys. Maybe if we have time at the end, I can mention L'Hopital's rule. We don't have L'Hopital's rules in the assignment, so you don't need to worry about it. This is the graph. So it's a sine graph which decays because it's being divided by x. So the bigger the x, effectively decays to 0. But we're interested in what happens when x is 0. So let's look at these numbers. So as x gets closer and closer and closer to 0, y gets closer and closer to 1. As get closer, closer, closer to 1. So when x is 0.09, y is 0.9987. When it's 0.077, it's 999. Get closer, closer, and closer. Except when we actually reach 0, where it is undefined again. But we can safely say that the closer we get to 0, the closer we get to 1. That is, limit of sine x over x is 1. And this is a very important, this is called I forgot what it's called, sorry. It's a special limit, basically. The assignment is not yet on the website. Professor Lvovsky is just giving it a final read at the moment. We had a few final reads. Another important limit is this one. Well, I mean, it could be limit of h tends to 0, sine h divided by h. It's still going to be 1. It doesn't matter. The name of the variable doesn't play a role here. We are going to use this to prove this, to solve problem 2. So I'm just introducing you to some limits, some important limits. The second very important limit that we are going to do, that as x tends to 0, the value of 1 minus cosine x divided by x is 0. It does, absolutely. It absolutely does justify the small angle approximation from x. So let's look at the graph of 1 minus cos x over x. And we can see that, well, it kind of passes through 0, 0, but obviously x cannot be 0 because you cannot divide by 0. So let's have a look. As x approaches 0, y also approaches 0, except in the middle where it's undefined. So we can say that as x approaches 0, the value of this expression approaches to 0 as well. And this is also a very important limit that we are going to use. So let's have a look. Find the derivatives of sine x and sine 4x from the first principles. So we write down f of x is sine x. Sine x. F of x plus h is sine x plus h. And you already know that this can be written as sine x cos h plus cos x sine h. This is from the previous assignment. And now we write down the derivative. So the derivative of x is equal to the limit as h tends to 0 of this minus this, of f of x plus h minus f of x. So sine x cos h plus cos x sine h minus sine x over h. We simplify that. We combine the like terms. So we combine this term and this term. There's going to be sine x cos h minus 1 divided by h. Now, plus cos x sine h divided by h. Okay? But we've already seen that this expression, as h tends to 0, this expression tends to 1. That is the previous result. We use that. As h tends to 0, this expression tends to 1. So this tends to 1. And we've already seen that this expression, well, it was 1 minus cos x. But, I mean, all you need to do is just take minus here. And this becomes minus, and this becomes plus. This is the expression, and this expression tends to 0. 0. So this is 0 times sine x plus 1 times cos x. So 0 times sine x plus 1 times cos x. And the answer, of course, is cos x. So that's a very important result. So effectively, what we are saying is that the derivative of sine x is cos x. You can also use Mayer approximation to prove the derivative. Not entirely sure how you would do that. Maybe, but yeah, maybe if it comes to me. Small angle approximation of to prove that the derivative of sine x is cos x. Yeah, not. I don't immediately know how to do this, but maybe. Okay, so just move this a little bit. So in a similar fashion, we can find the derivative of sine 4x from the first principles. So we're going to write down that f of x is equal to sine 4x. Then f of x plus h is sine 4x plus 4h. And yet again, we do the same stuff. We do the sine 4x cos 4h. By the way, the proof of these limits is quite extraordinary. It's difficult. It's quite cool. So if you do have a chance, study these limits and try to explain how they work effectively. And okay, let's move on. So what we have here is so plus cos 4x sine 4h. This is just using the property of sine. And we write down that the derivative of x is equal to sine 4x cos 4h plus cos 4x sine 4h minus sine 4x divided by h. Forgot the limit. H tends to 0 equals limit as h tends to 0 of, now combining the same terms again, so sine 4x open bracket. I'm going to be smarter this time. So what I'm going to do is I'm going to take minus sine 4x out of the bracket. I'm allowed to do that. So I'm going to have minus cos 4h plus 1. So I'll do it straight away. So I'm taking these two, the first and third one. And then so divided by h plus cos 4x sine 4h divided by h. Now, if we look at these expressions, now we have cos. So there's a few tricks here that you can do. Well, you know, if h tends to 0, that means 4h also tends to 0. So instead of h equals 0, we can use 4h tends to 0. Why we need this? Because we have 4h here, but not h. But it's easily amendable. We put a 4 here, and we put a 4 here. If we multiply the top and bottom by 4, the fraction does not change. And we do the same thing here. We multiply the top and the bottom by 4. And now we see the familiar limits. This limit is 1. This tends, 0 tends to 0. And this tends to 1. So this is 0, and this is 4 cos 4x. So the derivative of sine 4x is 4 cos 4x. You can use the chain rule by all means, but this exercises do it from the first principles. So the derivative of sine 4x is 4 cos 4x. Okay. 4 cos 4x. So a lot of the assignment would be find the same thing using the product rule, the chain rule, and from the first principles. Yeah, so you can find the same stuff using various methods. It is important for you to understand, to be able to do this. Also, there's an interesting thing. Let's say if the derivative of sine x is cos x, then the derivative of sine 2x is 2 cos 2x. So effectively, if you double the argument, you double the derivative. And this has a very elegant explanation. If you take the graph, I'm just going to use Desmos for this. I do recommend you using that a lot. It's a fantastic tool. So y equals sine x. Okay, y equals sine x. And you can see that if you draw y equals sine 2x, it's a squeezed version of the graph. And as the graph gets squeezed, the gradient doubles. If you double the argument, if you double this, the gradient doubles because the graph is squashed. So let's do this. Let's put this into the notes. As the gradient doubles, sorry, when the argument doubles. And this is true for all functions, not just trigonometric functions. Like x squared, if you do 2x squared, you're going to have a steeper graph, 2 times steeper, in fact. So when the argument doubles, the graph becomes twice as steep. So the gradient doubles. Okay, so that's that. And then they said, use the previous result to find the derivative of sine squared x. Sine squared x. So, well, we need some trigonometric identities. And we know that sine squared x you need to simplify it. So we take cos 2x. We know that cos 2x is equal to 1 minus 2 sine squared x. So sine squared x is equal to a half minus a half cos x. Cos 2x, sorry. That's a very important identity. Yeah, I hope no one has a problem with this. I mean, I'm just rearranging sine squared x to get this. So sine squared x is 1/2 minus 1/2 cos 2x. And yeah, I shouldn't have said to use the previous result. It's not. I'll just cross this out. Because we actually didn't find the cosine, we did the sine. And if you want to find the derivative, sine squared x derivative, it's going to be 1/2 minus a half cos 2x derivative. So the derivative of a half is 0 minus a half, this half stays, and then the derivative of cos 2x. The derivative of cos 2x is unsurprisingly minus 2 sine 2x. So we're going to use that. So it's going to be minus 2 sine 2x. We simplify. This is going to be 1, so it's going to be sine 2x. And, well, if they ask you to put it in terms of sine, cosine and sine, then this is what they do in the assignment. I think that's problem 1. It's going to be 2 sine x cos x. And this would be the answer. So you have a very similar problem in the assignment. I'm very sorry that you can't see the assignment yet. It will be there today. Okay. Right, so halfway through, and we are in problem 4. Okay, small angle. Small angle does come from Maclaurin. I mean, there are other ways to prove it. Problem 4. Use the product rule to find the derivative of this. Expand the brackets and find the derivative without using the product rule. Compare the answers. So the product rule, if you are unfamiliar with the product rule, please type 0. Okay. Oh, wow, quite a lot of zeros. Okay. Well, we are in the assignment. We teach you the product rule. It is a year 13 topic. If you're not doing further maths, if you're doing further maths, you should do it. Okay. Another question then. If you are unfamiliar with the fact that the derivative of x to the power n is n times x to the power n minus 1. If you're unfamiliar with this, please type 0. One, two, three, 4, 5. Yes, thank you for following the instructions. You don't need to type 1. just a few of you aren't familiar. Okay, we have done videos on this. Well, not video, sorry, we haven't done videos. We have posted in the assignment, we have videos on this. So please study the videos carefully when the assignment is going to be up. But not too many of you. So most of you are familiar, which is good. So those of you who are unfamiliar, sorry, but you will need to study this. It's not a difficult thing, but it's pretty much it's there. I've said it. So for example, the derivative of x cubed is going to be 3x to the power 3 minus 2, which is squared, which is actually exactly what we got in the first question. 3x squared. The derivative of x cubed is 3x squared. It's how fast the function is changing. So the product rule says that if you have the product of two functions, let's say u and v, it's equal to the product of the first function multiplied by the second function plus this first function times the derivative of the second function. This is the product rule. So let's try to use it. Let's have x squared multiplied by sine x, and you differentiate it. So the first function is x squared. This is u, and this is v. So this is going to be x squared prime sine x plus x squared multiplied by the derivative of sine x. So this is how you use the product rule. It's quite simple, quite straightforward. There's nothing extraordinary here. Then you find the derivative of x squared. It's going to be 2x sine x plus x squared times the derivative of sine. The derivative of sine, as we have learned, it's cosine. So x squared cosine x. This is how you use the product rule. So the derivative of this is this. Okay. And we're going to use the product rule to find the derivative of this. So we have x squared minus 3x x to the power 3 minus 8x prime, so the derivative. So we take the first function, derivative of the first function, times the derivative of the second function. Oh, sorry, times the second function, plus the first function, x squared minus 3x, times the derivative of the second function. The derivative of this is 2x minus 3, using this formula. The derivative of x squared is 2x. The derivative of x to the power 1 is just 1, multiplied by x cubed minus 8x plus x squared minus 3x multiplied by 3x squared minus 8. Now, because normally you don't have to simplify that, but we will, because we will be comparing it to the other result. So this is going to be 2x to the power 4 minus 16x squared minus 3x cubed plus 24x plus 3x to the power 4 minus 8x squared minus 9x cubed plus 24x. Okay, plus 24x. And we can simplify that. So combining the 4's, so 5x to the power 4. And
oh, Godfather. Are you okay, Sonia?
oh, can you please mute yourself? Okay. And the cubes is minus 12x cubed. And then the squares, so that's minus 24x squared. Then the, oh wow, so no term without an x, so plus 48. 8x. So that's the derivative using the product rule. Now let's try finding the derivative using the standard way. So just using this formula. So we expand the brackets. It is a bit tedious. I'll try to do it quickly. X to the power 5. So I'm taking f of x, yeah? F of x. I'm just taking this and expanding. X to the power 5 minus 8x cubed minus 3x to the power 4 plus 24x squared. We don't have any like terms, so we find the derivative, and it's going to be 5x to the power 4 minus 24x squared minus 12x cubed plus 48x. This is the moment of truth, whether I've messed it up or not. And I haven't. It's the same expression. It's the same expression here and here. So we obtained the same result by using the chain rule, the product rule, and by using the by just expanding the brackets and doing it normally, and which is great. Okay, just give me a moment with that. It's a tough one. And that's probably even tougher. Let's talk about this problem first. Let's go to problem 7. A very big section on differentiation is optimizing. Optimizing means finding the minimum or maximum value. So for example, if you are a business and you want to minimize your costs, or you want to maximize your profit. Okay, minimizing costs is a rubbish idea, because to minimize your cost, you just need to close down. Then the cost is zero. You want to maximize your profit, or sometimes you want to maximize your revenue, which is sometimes a good idea, not always. Okay. And if you are a builder, for example, a construction worker, you want to, an engineer, you want to minimize the amount of materials you're using, or maximize. So let's say you have 17 materials. What's the biggest thing you can build? Okay, so you can use differentiation to answer those questions. And differentiation gives you a very elegant solution to that. So let's look into some stuff. So let's say you have a function. You have a function which is continuous and differentiable. Continuous means that it doesn't break anywhere, it doesn't have holes in. And differentiable means you can find the derivative. So I'll give you an example of a non-continuous function. So for example, this function is a non-continuous function. It has a breaking point here. It's a non-continuous function. And this function is non-differentiable, because at this point, it's impossible to calculate the gradient. And at this point, it's impossible to calculate the gradient. So this is what we call a non-differentiable function. I mean, it's non-differentiable only at 2 points, at the breaking points. So it's a smooth function. Now, if you have if the function is defined on an interval from A to B, for example, B, the question is, what is the maximum and minimum value of a function, of this function, on the interval AB? So the question you're trying to answer, what is the minimum and maximum value? What are the minimum and maximum values of f of x on the interval a less than or equal to x less than or equal to b. And well, actually, you can have the minimum and maximum values, min and maximum values only occur at A or B, at x equals A or x equals B. You can see that the minimum value is actually here. This is the minimum value of the function on the interval. So this is the f min. Or at points where the derivative is zero. This is a theorem of maximum value of a function on an interval, but the idea is that the maximum value, you can see it's here. This is the maximum value. This is a local minimum. So it's locally it's a minimum, but it's not a minimum. And these are the points where the derivative is 0. So the gradient is 0. So the derivative is 0. And here the derivative is 0. Okay, this is y equals f of x. These are points where the derivative is 0. And these are the ends of the interval. So the minimum value can occur at the end of the interval, sorry, or at the local minimum and maximum. The aim of the assignment is to teach you differentiation. So you don't need to know it, but you need to have an open heart and be able to absorb differentiation. Of course, those of you who have done differentiation will find it easier. Those of you who haven't done differentiation yet will find it more challenging. So maybe it's just worth mentioning to your tutor before you submit the assignment that it's the first time ever you're doing differentiation. So we'll be lenient to you. Okay, so the gradient of the graph is 0 means the derivative is 0, because the gradient is the derivative. Once again, the derivative of a graph is the gradient of the graph at that point. And if the derivative is 0, that means the gradient is 0. And the point can be a minimum or a maximum if the gradient is 0. But if we're talking about the minimum or maximum value of a function, it can also occur at the interval. So for example, let's take a function like this. The minimum is here, the maximum is here. There's no points where there's no local minimum or maximum. All right, on a scale of 0 to 10, how well do you understand this? Lots of 10s. Okay, don't be shy, please. Okay. In the assignment, you will find a lot of videos explaining this. So please do not be discouraged that you don't understand it now. Yeah, I'm jumping into it. I'm jumping into the middle of the assignment, literally. So those of you who wrote 3s, so probably the ones that haven't done differentiation yet. Okay, so please don't feel discouraged, don't feel overwhelmed. There are a lot of videos explaining this, and you have the support of your fantastic tutors. So this week, when you have the tutoring session, ask as many questions as you can. The derivative is the gradient of a function, and the minimum and maximum can occur here. Okay, so let's have a look. Basically, what is the question? What are the dimensions of the largest rectangle that can be placed in the triangle above? Basically, what happens? We can change the rectangle like this one. Is this bigger than this by area? Or perhaps this? Or perhaps we want to make it as long as possible. Well, that doesn't seem to work, because if you do it as long as possible, the area is going to be 0. So it's probably somewhere in the middle. We don't actually know where it's going to be, but okay. Basically, the question is, what is the maximum area? And we can say that, let's say that this side of the triangle this side of the triangle is x. And x can take any value between 0 and 24. So we already have the limits for x. So we can start plotting. So x can change from 0 to 24. 0 to 24. And this will be the area of the rectangle. So when x is 0, what is the area of the rectangle? The assignment is being released today. We're just finishing off the final bits. What is the area of the rectangle if x is 0? 0, of course, because the rectangle would look like this. Okay, I'm just going to make it red. The rectangle is going to be like this, so the area is going to be 0. So when x is 0, when x is 24, what is the area of the rectangle? 0 as well. That's nice. So we know that it's not at the ends of the interval, because at the ends of the interval, it's minimum, it's 0. So somewhere in between, any point in between, actually, it's not 0. So the area is going to look like this. So it will be increasing, then reaches a maximum point, and then decreases. So somewhere here, we have a maximum value for the area. And the question is to find this x. Okay, so we need to express the area in terms of x. Area in terms of x. Express area in terms of x. Of x. And this might be the most challenging bit of this question, like express area in terms of x, because the rest is easy. Okay, so let's suppose that this is x. This is x as well. For simplicity, I'm going to write that this is y. This is going to be 24 minus x, because this is x and this is 24, so this is 24 minus x. And this side is 18 minus y. We can note that these triangles are similar. These triangles are similar. Therefore, we can write down that the ratio of these sides, actually, I don't need that. I can do it much simpler. I'm going to notice that this triangle is similar to this triangle. And using the similarity of these triangles, I'm going to write down that the ratio of 18 to y, so 18 to y, is the same as the ratio of 24 to 24 minus x. 18 to y is the same as 24 to 24 minus x. So I hope that makes sense. This is like the scale factor. The scale factor is, so the one triangle is an enlarged version of the other. So this is like the scale factor of the enlargement. So we have rearranged this to find y is equal to 18 times 24 minus x using multiplication symbol is a bad idea. 18 times 24 minus x divided by 24. Simplify, so this is 3, this is 4. So 3/4 times 24, that's 18. 18 minus 3/4 x. And we know that the area is x times y. Area is x times y. And therefore it's x multiplied by 18 minus 3/4 x. I'm expanding the brackets. So it's 18x minus 3/4 of x squared. And actually what you can do is you can actually just plot this. Y equals 18x minus 3/4 of x squared. And immediately you can see then this is the graph, so 0, 0, 24, 0. So that makes perfect sense. Let's find where it's maximum. It's maximum here, and it's actually equal to 12. So exactly halfway. But we'll prove that. We'll prove that using calculus, of course. Okay, but this gives us a nice nice visualization of the process. So this is the area, and this is x. So quite nice, quite a nice curve. Okay, so moving on, we need to find the derivative of a with respect to x. So we find the derivative of a, and this is going to be 18 minus 3/4. So it's going to be 3/4 times 2x, so 3/2x, the derivative of that. And this has to equal to 0, because when a is maximum, a prime is 0. Or minimum, maximum or minimum. This is a prime is 0. So what we're going to do is we're saying that this is equal to 0. So 18 minus 3/2 x is equal to 0. So this 18 equals 3/2 x. So x is equal to 12. So area is maximum when x is 12. And let's find that area. So area is equal to 18 times 12 minus 3/4 times 12 squared, which is 108. 108. Okay. So differentiation allows you to solve problems like this. very important problems on optimization. Like economists use that a lot. Okay. So this, and you will have there's a question in the assignment about finding, there are two questions actually, finding the maximum possible area of a rectangle and the maximum possible area of a triangle as well. So these are quite elegant and quite nice. I'm not sure if I want to do this one, but yeah, okay. Problem 6, find the equation of a straight line which is tangent to the curve y equals x squared minus 2x minus 1, modulus x minus 1. Now, one of the toughest things that you need to do here is actually plot this graph. But you have a fantastic tool to plot any graph. So feel free to use it. So y equals x squared minus 2 modulus. So y equals x squared minus 2 modulus x minus 1. Is that correct? X squared minus 2 modulus x minus 1. Okay, so we need a graph that is tangent to both. Oh, sorry, which is tangent to the curve in 2 distinct points. Well, I think there's only one option for this. So the line has to go something like this. And, well, you kind of see where it goes. Let's try connecting these two points. 2, 2. So a straight line going through the two points is going to be 2x minus 2 modulus. So the definition of a modulus x is equal to x if x is greater or equal 0, and it's equal to minus x if x is less than 0. This is the definition. Can be a mouthful, but what you need to understand that the modulus is the distance of the point from 0. So this is 0, and let's say the point 7. So modulus of 7 is 7, because the distance from 7 to 0 is 7. Okay. If you take minus 8, the modulus of minus 8 is 8, because the distance is equal to 8 still. Okay. So basically what the modulus does, if the number is positive, it stays as it is. If it's negative, it changes to the opposite. Does that make sense? No. Okay. We will have a whole assignment on the modulus, so don't worry. And you do not have modulus in this assignment. Okay. This question used to be in the assignment. It was removed yesterday. That's why we're doing it now. Now, but just looking at the graph and just seeing that the graph goes like this, There's only one way you can draw the there's only one way you can draw. That's not it. There's only one way okay. There's only one way you can draw it, and that is something like this. Which works amazingly well. Let's try to figure out the equation of this graph. Well, it's a straight line graph. The gradient is clearly 2. The gradient is 2. And the y-intercept is -2. C is -2. So y is equal to 2x minus 2. Let's check it out. So we draw the graph of y equals 2x minus 2. And voila, it is the gradient at 2 distinct points. Okay, 2 distinct points. Yeah. And just like this, you can do it. I mean, this is a terrible shortcut. Of course, you can do it analytically. Doing it analytically is difficult. It's difficult. There is an example in the assignment. There is an example where it's done analytically. A very similar problem done analytically. But yeah. Okay, so find the equation of a straight line which is tangent to the curve in 2 distinct points, and the answer is by graphing. If you want to do something by graphing, you do need to put in an explanation for that. So y is equal to 2x minus 2. But then you need to confirm that it is true. Well, yeah, one of them could be just plotting this. Okay, don't want to go too deep into that. Now, the last problem that I wanted to discuss with you is horrible. It's not in the, nothing like this is in the assignment. So you should not worry that you will face something like that. Okay. What I want to demonstrate by doing this problem is that you can pretty much find the derivative of any function, no matter how difficult it looks like, how difficult it looks. Now, initially I wanted to put that in, but then I realized, well, you'll hate me. So let's give it a go and just watch how I unwrap this monster into something doable, into something solvable. So I'm not going to do any simplifications. So I will be using the chain rule, which you might not be familiar with. And I will be using the quotient rule, as well as the product rule. So let's have a look. So first, to find the derivative, I'm going to use the chain rule, because there's a square here. And I'm going to use the chain rule. So the chain rule says that I would just have to treat this as another function. So it's g squared. So it's going to be 2 6 cos x squared minus 2x divided by x sine x multiplied by the derivative of the inside function. So we refer to this as the inside function. Inside, and this is the outside. Outside. So what we do is we find the derivative of the outside function. This is the derivative of the outside function. And times the derivative of the inside function. So a very detailed explanation of this is given in the assignment. So the derivative of the inside function, so 6 cos x squared minus 2x divided by x sine x prime. Now, we don't need to do anything with this because all we need to do is this. So what I'm going to do is I'm going to write it out separately. I'm going to write it out separately. So here I will continue this once we're done. I'm going to write this out separately. I'm going to use the quotient rule. The quotient rule looks like this. If you have a derivative of a fraction, it's u strife v minus u v strife divided by v squared. So it's going to be x sine x squared. And it's going to be 6 cos x squared minus 2x derivative x sine x minus 6 cos x squared minus 2x x sine x derivative. So using the quotient rule. You will have the quotient rule and the chain rule for the assignments, but you will not have this questions like this. Now you find the derivative of this. So here I find the derivative of this. I use the chain rule again. So it's going to be 6. Sorry, it's actually going to be 12. 12 because the 2 comes out. 12x multiplied by sine and minus sine x squared. Okay, I think I need to explain this better. So you're going to be 6 multiplied by the derivative of the outside function. The outside function is cosine. So the derivative of cosine is minus sine x squared. Okay, minus sine x squared. Multiplied by the derivative of the inside function. The inside function is 2x. Minus 2. And this is multiplied by x sine x. Minus, now this doesn't change. So 6 cos x squared minus 2x. And then do we find the derivative of it? This is the product rule again, and we've actually done it. So it's going to be 1 sine x plus x cos x. Div all over x sine x squared. And now all I need to do is copy that and put it here. Oh no. Okay. And I also need that. And this is the answer. I mean, do look through this. I mean, it took me what, 4 minutes, 5 minutes to do this. So what I'm doing here, so first I'm using the chain rule here, chain rule, rule. Then I'm using the quotient rule. Then here I'm using the product rule. And here I'm using the chain rule again. So a combination of chain, quotient, and product rule gives you powers to do any sort of function, no matter how difficult. Okay. Okay, we're coming up to the end of the session. Now, those of you who are not familiar with differentiation, I want to go through some very, very basic stuff right now. So those of you who have already done differentiation, you feel free to switch off. And those who are for whom differentiation is very new, can you just stay for another few minutes so I can explain some of the very basic stuff of differentiation. Yeah, I mean now. Okay, you can. So those of you who know differentiation, you're welcome. And just to see, well, first of all, I'd like to see how many of you. Right. Right. Those who don't know, no, I'm going to do the very, very basic. Like what is a differentiation? How to differentiate x cubed, for example? How to differentiate x squared? Okay. Right. So how many people are still in the 15 people? Okay. So the very, very basic stuff. Yes, guys. So the guys who stayed behind. So I assume you haven't done differentiation at all. So what is differentiation? Well, there is the formula that is introduced in year 12. And the formula is that the function, if you have a function, let's say y is equal to, well, let's do a simple function, 3x plus 2. The derivative tells you the gradient of the function. So what's the gradient of this function? 3, of course. So the derivative is 3 because the gradient is 3. But for a different function, let's say for a function y equals x squared, the gradient depends on x, because for different values of x, the gradient is going to be different. So if we draw y equals x squared, you can see that the gradient at different points is different. And as a matter of fact, the gradient for this function is equal to 2x. So when x is 0, the gradient is 0. When x is 1, the gradient is 2. So the gradient is 2. The gradient here is 2. When x is 2, the gradient is 8. Let's talk about this. Like when x is 0, the gradient is 0 because it goes like this. When x is 1, the gradient is 2. When x is 2, the gradient is 4. And you can, it's sort of believable. I'm not proving it, but it's believable. It looks like it is like that. And the formula that if y is equal to x to the power of n, the gradient of that function is going to be n multiplied by x to the power n minus 1. So if y is x to the power 4, y prime, the gradient, is, somebody type in the chat using this formula, 4x cubed. Yes, 4x cubed. If y is equal to, now this is a bit trickier, is x to the power minus 2, y prime still works. Minus 2x to the power minus 3. Yes, minus 2x to the power minus 3. Let's do a more trickier one. Y equals square root of x. What is the gradient? 1/2 x to the power minus 1/2, exactly. So 1/2 x to the power minus 1/2. And you can simplify this to 1/2 root x. So the gradient of this function is this. Well, we call it the gradient function. It tells you the gradient at any, for any x. The gradient for any x. Okay. And there's a simple rule that if you have a linear combination, don't let the word linear combination scare you. So let's say 3x squared plus 7x cubed minus 3 square root of x. The derivative is going to be 6x, because x to the power, we don't touch the 3 stays. And 6x plus 21x squared minus 3/2 root x. Okay. And one final thing. If y equals 7, what is y prime? Y equals 7 is a graph, and the gradient of that graph is 0, of course, because the gradient of a horizontal line is 0. This is a horizontal line. Horizontal line. Line. And the gradient of the horizontal line is 0. So in fact, if y equals c, where c is a constant, y prime is 0. Now, very often you will see that the derivative is written like this. Y prime is equal to dy over dx. So whenever you see dy over dx, it is the same thing. It's the gradient of the graph at point x. Is that making sense? It is delta y over delta x. It is, absolutely. It's just the definition is dy over dx is the limit of delta y over delta x as delta x tends to 0. So delta means quite big and d means infinitely small. So it's an infinitely small increment. All right. I hope that clears things up. Was that useful? Please tell me the last 5 minutes, was that useful to you? Okay. Right. Welcome. Okay. Then good luck with the assignment. It is due on the 26th of December. And I'll see you next week. I will be doing this webinar every week. So please, if you have questions, please let me know. And otherwise, right. Have a good evening. You're welcome.